So believe it or not, organic chemistry is not as hard as it may seem. And in fact, in order to get an A+ in organic chemistry, there are just a few simple rules and principles you need to know in order to master organic chemistry. And in this video, I want to go over the most important rule you need to know for organic chemistry. And it's this. Let's say we have this negatively charged electron with its negative electron density, this negative charge density. Something important to note is that nature hates strong localized charge density. So whenever we have this kind of charge density, nature likes to take that charge density and to delocalize it. So what do I mean? Rather than having that negative charge over this region, it likes to take that negative charge and to spread it out over a larger region. So now we have that negative charge over a larger region. So again, originally this electron had a certain amount of charge in this given volume, but nature hates this strong localized high charge density region. So what it likes to do is it likes to take that charge and it likes to delocalize it. It likes to take that charge and it likes to spread it out. It likes to take that charge and to spread it out over a larger volume region. So when it does that, now there's a lower charge density. It's the same amount of charge, but over a larger volume. So there's a smaller charge density. So there's a low charge density, and this is energetically favorable. This is stable, and nature likes doing this. Nature hates this localized charge, and nature would really hate if we took this negative charge from this electron density and to localize it, to take this charge and to squish it into a small region. So that would be localizing the charge. If we took this electron density and to localize it into this small, squishing it into this small region, that's very energetically unfavorable. This is very unstable. This is a high charge density. That same amount of charge is now localized and squished into a small volume. So this is very energetically unfavorable. This is very unstable. So what nature likes to do is it likes to take that charge and it likes to go in the opposite direction. It likes to take that charge and it likes to delocalize it. Spread it out so we have a weaker charge density. This is energetically favorable and this is stable. So this rule explains every other rule I'm going to talk about in my other videos. So what do I mean when I say this? So let's do an example. Maybe this will make more sense. So let's say we have this compound, this carbon anion with this negative charge. This isn't very stable because we have this formal charge of -1 localized on this carbon. So we have a lot of negative charge density localized on this carbon, which we said isn't stable. We don't like localized high charge dense regions. So what this compound will do, what nature will naturally do, is it'll go through a resonance structure. It'll go through a resonance structure that looks like this. So now the charge density is on this oxygen, so we go through a resonance structure. But in reality, what's going on is it creates this hybrid resonance structure that looks like this. So now instead of that negative charge localized onto this carbon, or instead of that negative charge localized on this oxygen, now that formal charge of -1 is now delocalized. It's delocalized and spread out over a larger volume. So now instead of that charge localized in one region with a high charge density or localized in this region with a high charge density, now it's spread out throughout this entire region of the atom, the compound. So now we have a low charge density, which is stable. This is energetically favorable. So nature, that's why we go through resonance. That's why we go through these resonance structures, because we delocalize this negative charge rather than this negative charge being strongly localized in a high densely charged region. Now it's delocalized. Now we spread it out over a larger volume. Same amount of charge, larger volume, smaller charge density. And this is stable and this is energetically favorable. So that explains why we do resonance. Because again, it's the same principle. We hate strong localized charge density. We like to take that charge and to delocalize it and to spread it over a larger region. So now let's say we had this compound. So if you haven't learned this mechanism yet, something important to note is we can hydrate this double bond. But when we hydrate this double bond, we could create one of two intermediates. We could either create an intermediate that looks like this, with the positively charged carbon here, or we could create an intermediate that looks like this. So which of these intermediates will we make? Once we have this, we could either form this intermediate or this intermediate. So we need to think about it. Which intermediate is more stable? Well, something important to note is this carbon is a double bonded with this oxygen. And we know this oxygen is very electronegative. This oxygen really likes electron density and hogs all that electron density, stealing that electron density, creating a partial positive on this carbon. So this carbon is partially positively charged. So let's draw that. This carbon is partially positively charged. And the same, this carbon is also partially positively charged. Because again, these oxygens are stealing the electron density. They're stealing the electron density, creating a lack of electrons, so therefore a partial positive. And something else important to note is this alkyl group is an electron donating group. It has a lot of carbon-hydrogen bonds with these orbitals with their negatively charged electrons, but just a key rule in organic chemistry, our alkyl groups are electron donating. So you can think of these alkyl groups as donating negative charge. So now that we know that, which of these structures seems more stable? Well, let's think about it. Remember, we hate strong localized charge. Whether it's localized positive charge or localized negative charge, that doesn't matter. We just hate charge that's localized and highly dense localized charge density regions. So now that, we know when we hydrate this double bond, we know we create either this intermediate, this positive carbon cation intermediate, or this carbon cation intermediate, this positively charged carbon intermediate. So let's think about it. When we create this positively charged carbocation intermediate, do we want that positive charge to be next to a partial positive charge? Well, no, that's not stable, because we already have a positively charged carbocation, a positively charged carbon with this positive density, charge density. So now if we have this positive charge density next to this other partial positive, now we have even more positive charge density. So this creates a region of high positive charge density, which is not stable. We hate having localized charge, whether in this example I was talking about localized negative charge, but it doesn't matter if it's negative or positive. Nature hates localized positive charge, so we don't want to create the positive charge here because we already have a partial positive here. So then we would have two positives nearby, and that's not stable. We would have a high positively charged region, which is not stable. However, if we create this intermediate, we create the partial positive here, which is further away from this positive, so it's a little more reasonable. And not just that, we have this negative electron donating region. So now so if we go through this pathway, we create this positively charged carbon here, but now we have this negative charge this region donating negative charge. And again, if we have positive and we're donating negative charge, they destroy each other. They'll neutralize each other, and essentially it will effectively lower this positiveness. If originally this was a certain amount of positiveness, but now this was a certain amount of positiveness donating some negative charge, it would make this less positive. It would make it less positive, so now we have lower charge density. Now we have a lower amount of charge, less positive charge, because this negative charge destroyed some of that positive charge. So this is stable. So this is the intermediate that makes sense. And again, it all has to do with this basic concept. So now one last thing is this rule really does describe all of organic chemistry. This rule of nature hating this localized charge explains all of organic chemistry. So let's say we have this compound. Let's say we have this carbon nucleophile with, again, this localized negative charge. And let's say we have this carbon electrophile with this carbocation. We know these are going to react. We know they're going to react, but why? Why do they react? Well, because we have localized negative charge, so we have localized negative charge, so we have strong charge density, negative charge density, which is not stable. And here we have localized positive charge density, so high positive charge density, which is not stable. However, if they react, these charges get destroyed. So now there's no charge density. If they react, we'd essentially create this compound. So originally we had this negative charge density, which is unstable, this positive charge density, which is unstable, but now that they react, those charges get destroyed and now there's no charge density. And again, we hate localized high charge density. We like to destroy charge density. And when they react, now there's no charge, so that's stable, that's energetically favorable. So that's why all reactions occur in organic chemistry. Organic chemistry, there's always a reaction with a negative, some kind of negative, whether it's a nucleophile or some kind of lone pair, reacting with some kind of positive, maybe some kind of electrophile or some empty p orbital. But again, so all reactions in organic chemistry stem from this this rule of wanting to destroy localized charge and wanting to delocalize it or just to get rid of charge altogether. So this rule explains all of organic chemistry and explains all reactions that occur in organic chemistry because of this basic concept.